So last week we said that unlike chemical engineering, where the number of atoms in the reactant and the product are conserved, you start with 1 carbon, you finish with 1 carbon. You start with 4 hydrogen, 2H2, you have to finish with 4 hydrogen. For example, CH4, that's 4 hydrogen. So unlike chemical reaction like this, in nuclear, the carbon can come in and no carbon will leave. Okay? So it will disappear on us. And same thing for the hydrogen. So then what is conserved in nuclear reaction so that we can complete the equation and find out what's the product? What's going to be conserved is the number of positive charge, the protons, which is written here, and the total number, the atomic mass, which is the neutron plus the protons. So those are the one that will be conserved. And we said a typical problem or example will be something like this, which you basically say, well, 13 plus 2, 15, I got 14, this must be 1, and over here the total was 27 plus 4, that's 31, I got 30 here, there must be 1 left over. So this is 1 and 1. So I go to the periodic table and find out what's the element that have 1 and 1. Or I could have 1 and 2, or I could have 12 and 35. Whatever the number, I will just go to the periodic table over here, and that will be in your exam. I'll put this in the midterm or the final. You'll just open here and you will figure, well, I got 1 and 1. Where is 1 and 1 in this scenario? So you come here, here is 1 and 1. Okay, and so this is the 1 and the 1, right? So the first one is the proton, and that's what makes this hydrogen. And the other one over here, it's basically the atomic mass. And for example, over here, 87 and 223. Well, 87 is the number of proton, and 223 is the total number. 56 and 137, all right? I guess what's confusing is that it's inverted in the periodic table than in the example. But obviously the smaller number is, the smaller number is the protons, and the bigger number is the total, obviously, right? Right? So when you see titanium 22 and 47, you tell yourself that's the number of proton and that's the total number. Right? Or 20 and 40 for calcium, for example, or 12 and 24 for magnesium, or sodium, or whatever the thing is. All right, you had a question? No? Okay. Let me download this so it's easier for us to open. Okay. So we finished by this slide last week. All right, so now look at this example. When you have basically some of the elements in nature are not stable, or basically they are radioactive. So as they are sitting there and they will keep emitting stuff. Okay, and while they are emitting stuff, by stuff I mean they will send electron or positron, or this, if they send, what is that? Helium. So if they send helium out, that's basically called alpha decay. And so obviously 2,4, when you send out 2 from here, you completely change your element. So radium basically become radon by injecting or basically emitting alpha particles. Okay. So in something like this, I can cover this for you and tell you what will happen over here, or I cover this one and say what element will happen if it goes through alpha decay. You also need to be able to, without me saying 2He4, I say if this element goes through alpha decay, find the product. So you just need to remember what is alpha decay and what is beta decay and positron decay. So alpha decay, you send alpha particle, which is helium nucleus, right? Beta decay is emitting an electron minus 1 and 0. That's electron, right? 0, how is it 0? It's because the mass is like almost nothing, right? And so anytime you have a beta decay, you will also get this guy, neutrino. So 0 and 0 basically, right? And so what is going on? He's telling you in that beta decay, a neutron in the nucleus become proton. So in order to come from neutron is neutral, to proton, which is positively charged, you basically do this by ejecting a negative charge out. Okay, and so that's what happened. So because he's emitting -1, he end up going from 82 to 83 while maintaining the same total mass. Right? That's the beta decay. The opposite of beta decay is positron decay, where you eject a positive charge out. Right? So all this activity basically change the element, and the way I will ask you to make sure that you know those stuff is that I will cover one of those things and tell you just do this simple mass to find out what's being ejected, or I will tell you this is going through beta decay, find out what will happen to it. Alright? Very good. So gamma decay, that is also some kind of radioactivity, but it does not change the element. Okay, so gamma decay does not change the mass or the atomic number, but it sends energy. And they use this in the gas industry, gas oil industry, how they have a gamma source on one side of the pipe, and they wait on the other side of the pipe with basically a receiver or a sensor that will measure how much radiation is coming through. Okay, and so if all the radiation goes through, that's one thing, but if the radiation is being blocked, you must have a lot of liquid, and they send the gamma radiation at different level, and they receive the signal, and by figuring out how much attenuation or loss in the radiation that's coming at those 3 different levels, they can even tell not just how much liquid and how much gas is in the pipe, but they can tell whether the liquid is oil or water, for example. So it's pretty cool for diagnostics to figure out what's the composition of the flow in the pipe, basically using gamma radiation. Right? And so you need a gamma source, you need something that emit gamma radiation all the time, basically. Right? So it's very dangerous, gamma radiation, obviously, if it's like strong, right? And the alpha decay actually is not strong at all, and they tell you a sheet of paper, just a sheet of paper like this, can block the alpha radiation, right? So some are dangerous and some are not. So while the elements are doing this radioactivity, losing gamma, losing beta radiation, gamma radiation, alpha radiation, whatever decay he's going through, obviously he's changing his composition, right? He's moving from sodium to helium, for example, or like he's basically changing his composition, right? So eventually all the molecules will change their composition after all of them emitted the particle that they are going through, their decay pattern. So by the end, there will be nothing left of the initial species. Okay? But this doesn't happen immediately. It takes time. And they measure that time by something called the half-life time. What's half-life time? It's when 50% of the population already went that change. Okay? So if I say the half-time is 5 minutes, then that means that in 5 minutes you will lose 50% of the population. It became something else. It became whatever the equation is saying. Alright? So sodium become neon. And then in another 5 minutes, you think we'll be done. No, in another 5 minutes, you lose 50% of the 50% that's left. So, and it goes and go, right? So it basically go exponentially until everything dies, right? So says speaking, it will happen at infinity, because every half time you lose half of the population that's remaining. So this can be expressed by this simple equation. Okay, and this weird number, it's not weird or anything. That is E, right? E to the power whatever, and so 1 over E actually. And so this equation is basically this curve, all right? And I can give you a problem that will ask you about the half-life time or ask you about n. So obviously there is 2 unknown over here. Okay, so he would say, how long does it take for that population to drop to 1/4 of the initial population? So n is the current number of atoms and n naught is the initial. So he wants only 25% to be left over. So that would be 1/4, right? 0.25. And you just try to find out the time. How long does it take for you to drop to 0.25? You can also get it graphically, but that's just for the easy numbers, right? When you go 0.5, obviously that is half-life time. You don't even need the calculation for this. If he said, how long does it take to reach 50% of the population to decay? You just get it from the table, right? And that is the time for half-life time. And you can see some of the elements like uranium 238, which we said 238 is the most common uranium we found. Unfortunately, we said we don't like it in our nuclear reactor. We like the 235, which is 0.7%, right? But look at the half-life time of uranium. How much is that number? Can anyone read? 10 to the power 9. So you immediately realize now what is the problem with nuclear power plants. The fuel rod that is, we started with 3.5, we said, of the good uranium, the 235, and what's the rest of the rod? What's the 96.5, the rest of the 100%, 3.5 good uranium. 96.5 is 238. And so after we finish eating the 235, okay, and sometimes this actually take forever to finish, like nuclear submarines basically don't really refuel. They put the fuel rods and the submarine is ready to go until basically it's ready to be decommissioned. You don't really need to refuel. But big nuclear reactor will need to be refueled. And so then what happened after we eat the 3.5 of the good uranium? The rest of the fuel rod is radioactive, and it's going to remain radioactive, sending alpha and gamma radiation for 10 to the power 9 years. So what's the problem? You got a radioactive spent, they call it spent fuel rod, that need to be stored somewhere safe so that people don't get the radiation, right? And so the problem become the storage of fuel rod, and so no one wanna take the fuel rods. And at one point they had this plan of building like a safe place in Nevada, I think, in the what mountain? I forgot what's the name of the mountain. Huh? Yeah, but Nevada didn't like the idea. They're like, no, we don't want the fuel rods. So the problem with nuclear energy, one of the problem is this, and we will see at the end, like we will discuss how do people solve this problem. Okay, but that is one of the problem. But you look at, for example, krypton, the half-life time is 76 minutes. So I'm always, when I see this, I always think, what's the problem with Superman then? You know, like only in just 76 minutes it will be over and he can be free. We cannot keep him more than 76 minutes and the krypton will be all gone, right? No, 50%, but I guess maybe you'll be strong enough if you get 50% of the krypton to decay for you. Right? Alright, so again, how do we deal with a problem like this? You either ask for the T or ask for, if he give you the T, if he tell you like in 3 hours of krypton, basically after 3 hours, and we are using krypton 87, you know, how much will be left? You put T here 3 hours. What's 3 hours? 3 times 60, right? Divided by 76 minutes, it has to be minute over minute. So you multiply this by this number, and this is e to power minus this number, and you get the new population. I need to tell you only 1/10 is left after 3 hours. Okay? So this table basically tells us what's the problem with radioactive fuel rod, spent fuel rod, but also this tell you, look at this, carbon 14, 5,000 here. Did you ever hear about carbon dating? So what is that? When they find like a new bone or an animal, and they can say, well, this animal lived, you know, 10,000 years ago or 1 million years ago. How do they do this? It's basically by looking at elements that went through decay, nuclear reaction, nuclear activity, and they can see how much is left over and how much has transformed. And from that they can tell, this thing must have started decaying at that point in time. Therefore that bone was from a human that lived, you know, how many thousands of years ago. Right? So now for this to work, they need to know the starting point. Right? They need to know that this decay started when this thing was alive. And so how could they tell this? Well, sometimes they get really lucky that the element that they are tracking their decay are trapped in another element that wouldn't exist otherwise. So there are certain conditions that basically know that this decay started exactly when the thing was alive, and it didn't exist before or after. Alright? So here's an example from our book. Right? Isotope, iodine 53135, decay by beta into xenon gas, determine the time required for the atom to be reduced by 90%. And that's the only confusing part in this example. What do you mean reduced by 90%? N over N naught should be 10%. That's the confusing part. So because it was reduced by 90%, then this is 0.1. So he's going to say this is equal 0.1, set the equation, get T and the T half-life time. He will go to the table and find out, or it will be given to him, find out what is the half-life time for iodine, and he basically, or actually it was given in the problem at one point. He will also give it to you. So it's 6.57 hours. So this 6.57 hours, so only one unknown T, and you get the number. Questions? Very good. So we said we are doing all this nuclear reaction just for this delta M, the fact that the mass will disappear on us. And when the mass disappear, you calculate this tiny change in the mass, you multiply by c squared, and that becomes the delta E. Alright? And so if you make the mass in kilogram and the c meter per second, you will get the E in joule. It's just that sometimes it's convenience to get the calculation in those units. What units? Atomic mass unit for the mass, and the energy in mega electrovolt. So electrovolt is like joule, it's an energy unit, and the M to make it mega basically. So in order to use this in atomic mass unit and get this thing in mega electrovolt, that number over here is this. The GZ, the conversion factor, is basically this. So this, you'll find out that this guy is probably the most useful one for you. Okay. Right, so if we want to stick to SI, then this M will be in kilogram and this E will be in joule, and the C is C square. So that's what, 300 multiplied by 10 to power 8. 300 multiplied by 10 to power 6. So C square would be 9 multiplied by 10 to power 16. So 8 and 8. I think you will, most of the time you will end up doing it in atomic mass unit and getting the energy in mega electrovolt. Alright? So that is another, rather than the equation, he put you the conversion in this table. Okay, so again, the most common is the mass is in atomic mass unit and the energy in mega electrovolt. Questions? Alright, so why nuclear engineering is really useful or valuable? And it's that table. So this is how much energy released per kilogram of fuel. So for chemical engineering, chemical reactor, sorry, this number is 10 to the power 7. And for our nuclear reactor that use fission, which is basically fission is like we break the atom, split it into two, and mass disappear in us. It's 10 to the power 12. So there is 10 to the power 5 reduction in mass. Okay? So imagine if a submarine, that's why there is nuclear submarines, because if we keep supplying submarines with diesel oil, they will never have a chance to submerge, kind of like every week, let's go up, get diesel, go down, diesel, go. Right? But you put nuclear fuel rod on them and they can just stay forever down there. So obviously if we can do fusion like the sun, that would be even better, but we can't so far, and we'll see why and what are they trying to do right now. But basically that is the big deal, that there is a lot of energy that's contained in the fission, basically. Right? So why we cannot do fusion so far? So that the sun basically generate, not the sun, all planets basically generate energy. All the stars generate energy by fusion. The gravity of the sun is so big that you can fuse 4 hydrogen atoms together and you make helium and this many positron, and when you calculate the mass of this side and that side, you'll find out there's a decrease in the mass as a result of this much, and that transfers to this much mega electrovolt for every reaction. So this is nice. What's nice about this? Yes, you get helium. You don't use radioactive material like uranium that has to stay alive for 10 to the power 9 years. So you get helium. That is great, right? Balloons. The nuclear reactor that will be working fusion will just have balloons on the side, basically to children for free. Everyone come and get your helium balloons, right? That would be the exhaust pipe, helium balloons. So now this is what's nice about this. There is nothing radioactive in this. What's bad about this is, or what's hard about doing this is, can you tell what's wrong, or like why this is super hard? So why? Yes, why? Yes, why? They resist each other because they are all positive, basically, right? But in fission, we split the atom by sending neutron, and neutron is neutral. So the neutron, you can shoot him and he will go through and break the thingy. But you try to put, those are basically 4 protons. You try to put 4 protons together and no, it will not come. But if they have huge gravity that can push them together, it will. Right? So it takes a lot of temperature in order to push them against each other. And so far, the material that we have in industry is not good enough to do this. So there's other nuclear fusion reaction. For example, this. I mean, they don't have to be 4H1. They could be like this, 1H2. So that's the heavy hydrogen. That's the one that make the heavy water, right? And you get this much energy. But the same problem, that you need to have them basically, this repulsive force need to be overcome, right? And so, because it takes a lot of temperature and we don't have material that take that temperature, I mean, even if you cover the nuclear, this is an experimental facility. European Union is doing this, and also the Russian had this. Actually is an old Russian design too. The idea is you use the best material ever, tungsten carbide, super whatever, right? So all the high temperature resisting material as much as you can. But still, even with this, what you need to do is keep them away from the wall by magnetic concentration, magnetic field and stuff. So if you keep this in the middle, maybe you can increase the temperature without melting the whole thing, right? And so obviously this is very attractive, and every now and then you will get a university president making an announcement. We made nuclear fusion in our lab, and the people will go and they will like come and see our data and stuff, and it's a big deal. But then they find out, no, you didn't really. There is calculation mistake somewhere. And the joke is always in fusion that it's always 10 years away, or like people are always. But it's very attractive. And recently, Lockheed Martin, they have the skunk work. This is it's called skunk work. It's basically the branch that made the Blackbird and made bunch of aeroplanes. Basically, they kind of start working on making small nuclear fusion reactor that they imagine would be great for aircraft carriers. So that tell you that industry is not this is not done just in research institute and national lab, but even industry are interested in trying to develop this. So what I'm trying to say is that although it started really long time ago and it's not done yet, but it may happen in your lifetime that people will manage to get fusion to happen in our facility. All right, and when this happens, that would be amazing, because we don't have to worry about spent fuel road ever again, right? But that's where we are basically now. So fission is easy to do, right? Because that's what's happening. You shoot 0 N1. What's 0 N1? Neutron. 0 charge, 1 mass basically. So you hit the good uranium 235. Unfortunately, it's very little of it in nature, but you hit it. There's other species also that can be hit 235 and plutonium, and 233, which is also rare. But the 238, that is the dominant uranium in nature, and thorium and plutonium 240, those are visionable by all, but only by high energy neutrons. So they require special reactor that's called fast reactor. So basically, and the Russian and Chinese are building those things, where and the USA has also research quality facility like this, where you can basically shoot 238 and end up generating energy out of it. But the majority of the nuclear reactor all over the world is using 235, and they shoot it with neutron, and then you end up with this, what, xenon and strontium, and 2 neutron. That's what's interesting. You get two neutrons. What's interesting is that then those two guys, you can lose one of them, he get dissipated, absorbed by something, but the other one will hit another one. And so if you keep one of them going, like every action generate one neutron that hit the other one, this is called chain reaction. And if that chain maintained at steady state, that reactor will always generate the same heat all the time. And then you can use that heat to boil water. And once the water boils, you got steam into a turbine, and you generate power, or you turn the propeller of the submarine, or whatever mechanical work you would like to do. But that is the key, that you have a chain reaction. Alright? And so the first time this actually happened was in was just before or during the Second World War. So they were really interested in making nuclear bomb, and they wanted to make chain reaction. But for a nuclear bomb, you don't just want one of them to make it. You want two of them to make it. Then 2 will hit 4, and 4 will hit 6, and 6 will hit, and then you have the big explosion. You don't just have, no, you just, right? Very good. So he is trying to show us why energy is generated. So he will calculate the mass here, the mass there, and turn the difference in the mass. Look at this. Here's the mass of every one of them. And we said because it's very tiny amount that disappear, you need to carry as many digits as you can. Alright? So you add all those things, and what happened? Minus 0.198. So the product have smaller mass than the reactant. So that mass that will disappear on us, you multiply by 3 to 10 to the power 8, and you get this much joule. Converting it, 184 mega electrovolt. Alright? So so a nice number to remember in your head is that fission generate 200 mega electrovolt. Maybe 184 instantaneously, but there is a decay heat that will keep going on. And so a nice number to put in our head is that it usually take every atom that you split of uranium-235, you will get 200 mega electrovolt generated. Alright? So that number is useful when you want to calculate, well, if I want to power Tulsa, Oklahoma, how much kilogram or gram actually of uranium I need to burn every day. Okay? So you need two numbers to do this calculation. How much energy is coming from the split of one atom, and that number is 200 mega electrovolt. And the second number that you need is what is the mass of one atom of uranium-235, and what is that mass? The molecular weight. The molecular weight of the U-235, right? Yes, that's constant. So the question is, what is that number? So the equation is delta E is delta M multiplied by C square, and the C, the speed of light, is 300 million meter per second, right? Or 310 to the power 6, or basically 3 to 10 to the power 8 square. So that's why it's 9 multiplied by 10 to the power 16 that we saw it before. Remember? Where did we see that? Here. 9 10 to the power 16, because it's 8 and 8, and 3 and 3 become 9. That's the equation. Okay? So that's an easy problem if I give it to you, right? But it requires you to have all those atomic mass units. Very good. So instead of, if I want to get this directly into this, I could actually use this. Remember this? Oh, sorry. What here? This one, atomic mass unit, mega electrovolt. Okay. So because this is a lot of energy actually, and that's why people thought that when they first found nuclear energy, they thought that this is gonna solve all our energy demand. Energy will be so cheap, basically. But it turned out that it's not really cheap, right? I mean, it's cheaper than other things, but it comes with its problem. The problem is how we can keep all that spent fuel robbed, and the problem also that we didn't suffer from yet, which is when we decommission those power plants, because no power plant will live forever. So all those nuclear power plants will have to be decommissioned at one point. And so to decommission the power plant when it's really old and you cannot maintain the turbine and the stuff anymore, you want to shut it down, that is going to be really expensive. And the company that will do this will have to charge the customer for doing this. Right? So the price for decommissioning will also be really high eventually. So here is the typical problem in the exams also. I always love to have a problem like this. How much 235 is required to produce 1 megawatt day? Megawatt day. This is like kilowatt hour, but way bigger. Megawatt day. So it's basically megawatt for a whole day. So I don't like this unit. I like joules, right? Or like mega electrovolt. We can turn the joule to mega electrovolt eventually, right? So 1 megawatt day, how can I turn this to joule? The mega 10 to the power 6. And then it becomes 10 to the power 6 watt day. And the watt day, that's not nice. I like watt second, which become joule. So I have to turn the day into second. So then, 24 hour times 60 times 60. You get how many joules are there, right? Okay, so we know now how many joules he wants. He wants to know how much is required. And so the magic number is again 200. Right? We said maybe 184 instantaneously and a little bit more decay heat, so for a total of 200. Right? So that is the 1 megawatt, and he's dividing over 200 mega electrovolt, and that is the conversion between mega electrovolt and joule. So 1 mega electrovolt is 1 to the power 1.6 10 to minus 13 joule. And so turning this from joule to how many atoms you want to break, this number become basically vision per second or atom per second. So now to figure out the mass of this, he need to just multiply by, this is how many atoms you want to break per second, so you need to multiply by the weight of each atom. So he's getting the mass of every atom. And he's basically saying, I know the molecular weight of U-235. It's 235, that's why it's called 235. Right? So 235 gram mole per atom. So how many atoms is in 1 mole? The Avogadro's number, 6.023 10 to the power 23. Okay? So when I was in high school, the Avogadro's number was like a total mystery for me. I just never understood what does it mean. What is that Avogadro's number? And the confusing part, I guess, for me is that I didn't understand what a mole is. I mean, if you understand a mole is, what is a mole, then you'll understand what's Avogadro's number. Okay? Right. So the mole is actually the quantity that have Avogadro's number. Right? So why is that useful? Because chemical reaction specifically, they happen by, give me 1 carbon atom, give me 1 O2 molecule. O2 is a molecule. Combine them, you get CO2. And so if we gonna make this reaction happen, someone needs to stand at the door through carbon atom, O2, carbon, O2, carbon, O2. Or, I mean, we are not gonna really do it every atom and every molecule, but you need to send 1 million carbon atom and 1 million O2 molecule. They will do it. So then a million and a million, I wish we know the mass, because the meter in the pipe can measure the mass. The shuttle that send the carbon to the furnace, he know the mass. And so you turn the molecule, number of molecule to mass by the molecular weight, which is the weight of 1 mole, which is the weight of this magic number, 6.023 10 to the power whatever. Okay? So it's a way to turn numbers into mass by defining the quantity, and then we would say, when you say C plus O2 makes CO2, that's 1 mole of C and 1 mole of O2. Or 1 kilomole of C and 1 kilomole of O2. Alright, so 235, that is the molecular weight, and this is how many atoms in 1 mole, and you divide over this, and that will be the gram per atom. Okay, so we know how many atoms we need, because we know how much energy is required and how much energy coming from breaking 1 atom. Alright, so you multiply this time the weight of 1 atom, and you will figure out how many gram you require per day. So 1 gram of 235 per day will generate 1 megawatt day. So that is 1 megawatt running for the whole day. Alright, so a big power plant like Jinx power plant, which generate almost 900, right, megawatt, 450 and 450, right, let's call it 1 gigawatt. So it requires 1 kilo. So 1 gram will generate 1 megawatt day. So 1 kilo, just 1 kilo of uranium-235 will replace this power plant for a whole day. Alright, with all the natural gas that's basically consumed. Okay, so it's very clear how how much energy is contained in nuclear reaction. Right? So here's a cartoon of what's happening. So 235 and neutron come and hit, split it into xenon and strontium, and 2 neutron generate, and hopefully one of them will make it to the next atom. Now this guy, in order to hit, you would think that he need to be really fast, but no, actually he needs to be a little bit slow so that he can get here and break it. So I guess what I'm trying to say is that this guy leaving, he's not ready. The guy leaving from the reaction, he's not ready to hit the next atom. Why? Not because he's slow, it's because he's fast. And so we need to slow him down first before he come and hit the next atom. And so that process requires a moderator. So the moderator material, and some reactor use graphene, like Chernobyl, the one that exploded on us in Russia, and some use light water, that's our water that we drink, so H2O, and some use heavy water, like it's not H2O, it's D2O. What's D? It's like the heavy hydrogen, it's the isotope of hydrogen. But all those moderators, basically their job is to slow down the neutron so he's ready for the next collision and absorption and breaking the atom. Alright? So you need a moderator in a nuclear reactor to slow down your neutron, and you need a coolant. Okay? And the coolant, what is a coolant? Well, when this happened, 200 megawatt mega electrovolt generated. You need to capture this energy before this thing melts. Okay? And that exactly what happened in Chernobyl. There wasn't enough cooling because that reaction grew very, very quickly. Okay? And this thing melted basically. So we need coolant and we need a moderator. What else do we need to make a nuclear reactor? We need to slow down this reaction if we want. Okay? Maybe we are in a submarine and the captain said, okay, we want to slow down, we don't need all this energy. So how do you slow down the energy generated from the nuclear reaction? You need to kill that neutron so that he doesn't make it to the next one. So the reaction rate, rather than maintain constant, you need to slow it down. So how do they do this? They insert poison rods, like neutron poison rods. Basically it's material that get in and absorb the neutrons, so they cannot make it to the next atom, right? So really a nuclear reactor is just like they have a kind of a lever, and let's inject the poison rod and they come in, the reaction die. So then you would say, well, so what's the problem with Chernobyl then? Why they didn't insert the rod and just kill the reaction? Well, their design, and that happened under Cold War environment where they wouldn't really share their design with anyone, and there was like secret cover on like how we generate energy. Their design was unstable to the extent that any increase in the reaction rate will result in increasing the reaction rate, basically. So the moment that the reaction go higher, that increase more and more and more, and so within few seconds the whole thing melted. There was no place for the rods to get in. The whole thing become just like a molten mess. All right. So so this is the design of most our reactor in the USA. Our moderator and our coolant are the same thing. It's water, light water. Okay, in Canada, most reactor in Canada, also the moderator and the reactor is the same thing, but they use heavy water. Okay, the difference between heavy water and light water is how much enrichment you need to operate. So if you have heavy water, and heavy water is expensive and you need a facility to make it, but if you have heavy water, then your uranium doesn't have to be enriched that high. You could even run with natural uranium. I mean, you bring it from the mine, make it fuel rod, put it in the reactor that run heavy water. So people running heavy water don't need enrichment program, but people running light water reactor, their fuel rod cannot be as mined. You have to enrich. You have to increase the percentage of the good uranium to higher level, 3.5 or higher. Alright? So then you'd argue, well, so why do you enrich? Well, if you're gonna make nuclear bombs anyway, you have an enrichment facility. So you might as well just like use the cheaper version of the nuclear reactor, which is light water. Right? But here what's nice again is that the water is working as the moderator and the coolant at the same time. So here is the atoms, and this is the fuel rod, and the fuel rod is basically sitting in bars like this, and water is everywhere around it. Bunch of fuel rods swimming in water. Alright? And why they break them into rods? So that they have water all over them. If they just make it one big cylinder of uranium, the atoms in the middle don't even have a chance to send their neutron to the water and come back, because they will get absorbed in the way. Right? So you need small rods so that you can have access to the moderator outside. So he's saying you just break it over here and he will bounce, go into the water, reduce its speed, and now he's ready. He will go in, get absorbed in the next atom and split it into two, and the journey continues. Alright? So they call it, this is a heterogeneous reactor core. Heterogeneous because what? The fuel rods are sitting in a sea of water. Homogeneous would be like, let's just have like one big chunk of uranium, right? And this what will contain or maintain a chain reaction for you. Right? Here he explained what is a moderator. I just said that, right? And if you're gonna use so here he's saying basically the natural uranium will work only if you have heavy water around, but for most other design you will have to enrich the fuel. Okay, so this is the part about the coolant. So again, we need always coolant to take all that extra heat. And so most nuclear accidents happen because of that coolant, that the coolant is not supplied in time to cool. Why wouldn't it be supplied in time? For example, in Japan, what happened in Japan? They built the reactor on the sea shore. Okay, Japan, earthquakes. So the building was supposed to sustain earthquakes, right? That's fine. But because we are next to the sea, that's excellent for cooling. But also, if you have an earthquake, the sea will have tsunami waves. Okay, we can fix that. Let's build a wall to protect the reactor from the tsunami wave. Okay, how high? Let's make it 7 meters. That's good enough for our design. No wave will come bigger than 7. No, it come at 13. Come at 13. And so the wave come, basically flood the thing, everything shut down. But they have a diesel engine sitting in the station. In case all power get cut, the diesel will run so that he can maintain or running the pumps that will maintain cooling the reactor, and then we'll be safe. So the whole problem is just we need to have a lot of water going to cool the reactor. And even look at this, those are the control rod. What's the control rod? We put them in and they kill the reaction. So the reaction is supposed to be dead, but there is also the decay heat. So even if you insert all of them correctly, they didn't do this in Chernobyl because they didn't have time. But in Japan, they claim they did, and they did actually. So the nuclear rod the control rod come in, shut down the reaction, but still the fuel rods are hot and they need to be cooled all the time. And without any pump running, and with the diesel in that diesel engine that was supposed to run, got flooded by the tsunami wave, and that's why he couldn't run. So basically the temperature got really high, the water split into hydrogen and oxygen, the hydrogen basically reacted, made an explosion, and the thing was on fire. The other reactor was damaged but not on fire, and so all we need is just like, let's bring water and cool them down. And so they decided, well, we need engineer to go in and install pump because the ocean is just there. We just need water to come from the ocean and cool. So they sent basically old engineers because they thought that they don't have enough life left on them. And so, or they volunteered. So volunteered basically old engineers only went in and they basically put the pumps and basically start cooling the reactor so that it can remain cooler. And so of course all that water went in the reactor and back into the sea. And so at that point there was concern that fish will eat that polluted water and you will end up with radioactive fish in the Walmart near your house, basically, eventually. But the point is, nuclear safety is all about that coolant. So if we just have redundancy of cooling circuits, a pumping system and a pumping system on battery and a pumping system on solar panel and a pumping system on wind turbine, and if you just have abundance of cooling circuits that's ready to cool, you will not have problem with decay heat. Okay, so that is the bottom line in in building a safe reactor. But you notice that all what I said right now are all active safety, meaning that it need a system to get in. It need a pump to get engaged. It need a battery to power something. Wouldn't it be nice if we build a nuclear reactor that is passively safe? Meaning that if humans are dead and no one can operate anything, he still would be safe? That would be nicer, right? So rather than something that you always need, guys, please come hold it. No, you want something that if no one hold, it is stable. Like you actually need to hold it to run. But if you get away, it doesn't run. That would be nicer. And a group of actually engineers from MIT, they came up with that design. They came up with a passively safe nuclear reactor. How the fuel in that reactor are sustained by a valve or a door that require always current. And when you cut the current, the door open and the fuel split or fall down and spill, and the reaction decrease because they are away from each other. So rather than always having to cool the thing, no, this one you always have to put your control or your hand or whatever to keep the reaction going. And when you shut down the electricity from it, it's basically open and there is no reaction happening. And what's even nicer, they solved the other problem, which is that we use only the 235 and we don't use the other uranium. So they actually made the design such that you can use the fuel rod all the way to the, like you can use more and more of the fuel rod. Okay. So this is the neutron poison rods or the control rods, and he explained to you that once they come in, they could come from the top or the bottom, but once they come in, they basically absorb the neutron, and there will be no more to go to the next level. So here is uranium as mined with only 0.7% of 235. They turn it into pellets, and those pellets are basically put in glading, or like just like a rod that they get inserted in, and you need to enrich it to be fuel rod. So he's saying the enrichment is basically to make it 3.5 to 5%. So if you are enriching less than 20%, that's called low enrichment. But if you go above 20%, that is high enrichment. And obviously you do this not for a nuclear reactor, but for a nuclear, yeah, you don't need that high level basically. Okay. So here is the first generation of uranium enrichment facility. So where is that? This is Oak Ridge, Tennessee. And so how we can enrich, how we can make the percentage of 235 increase? Well, we got 235 and 238. What's the difference between 235 and 238? That's 3. One of them is heavier than the other one. So if we send them in a configuration like this, the heavy one will keep going, and the lighter one will have a better chance to go to the holes. All of it, no, but a little bit more. So maybe after one of this, you will go from 0.7, you will find yourself here at 0.71. But then with a facility like this, you have more and more and more stage, and you go from 0.71 to 0.72 to 0.73 to 0.74, all the way to 3.5. Okay? So a facility like this is really big, and any country that will make something like this, I mean, you can see that facility from the sky basically, right? So the next generation was, see, those are people, and this is a centrifuge. And so they spin, and obviously when you spin like this, what happened? The heavy guys go to the side and the lighter one go to the middle, and you can pull the lighter one. And by the way, something you should have asked me about something. Uranium, that's That's a solid. How does all this thing happen? How does this happen? Not just, it's not good enough to turn it into a powder, no. You turn it into a gas by reacting it with something, right? So UF6. Okay, so now it's a gas, a heavier gas and lighter gas. By how much? By the difference between 238 and 235. Then lighter gas do all this magic. Okay, so a centrifuge basically, and there are a lot of them, right? Why? Because stage after stage after stage after stage, you go from this much to this much to this much to this much, right? And that's why in Iran, when they were like inspecting them, they wanted to say you cannot have this number of centrifuge. You have to limit their number, because as you add more and more, you will go from 3.5 to 10 to 20 to, right? So they had a cap on how many centrifuge you can have. All right.
What number is
So again, we are mechanical engineers, so we just know how to use the output of this thing rather than how to design it. Let's leave it for the nuclear reactor engineers to design this for us. But you just need to know that this is a big facility that require a lot of rows of centrifuge in order to increase the level. All right. Now the third generation is actually using lasers, and so using laser they could mark the heavy uranium from the lighter one, or increase its basically charge, and then you get bullets away from the flow. So now when they came up with this, an Australian company came with this, and immediately GE got the license for it. But there was a letter from the American, I'm a member of the American Physical Society, and so they wrote a letter to the US government saying that they should ban this, any research done on this technology, because the problem is this can be done in the lab in any university. Like, you don't, unlike all the previous technology that you need huge facility, this can be very small and you cannot detect it from airplane or submarine. All the other facilities require a huge amount of energy, and you'll be able to say, well, why do you have all this megawatt in that place, for example? You cannot hide it. You can, but it's hard. But this one is, and so they were split. That actually the physician or the physicists were split. People say, no, this is good for humanity, and we need to explore this because it makes nuclear energy cheaper. And the other group say, no, like you don't mess with fire. You cannot develop something that everyone can make a nuclear bomb in his house eventually. So we cannot basically use that technology, right? But basic technology is called SILEX, Australian Laser Enrichment Technology, and I guess Australia has like a lot of uranium. That's why they were interested. But it's basically labeling the molecules and then attracting them differently. But again, it's gas, right? All right. So here is the current available reactor design. The one that we most use in the USA is the one that use enriched uranium, and the coolant and the moderator are water, regular water. The one that Canada used, it's called CANDO design. Okay, and that CANDO design use natural uranium. You don't have to enrich, but then you will have to have heavy water as coolant and moderator. All right. The gas cooled there is a lot of gas cooled reactor in England, and so they would cool rather than with water. They will cool with CO2. Unfortunately, the CO2 is not a good moderator to slow down the neutrons, so they use graphite for it. Okay, and the light water graphite That's basically what Chernobyl was. The fast neutron reactor, those are the one that can burn 238. And so to burn 238, you need the moderator to become a molten liquid, basically molten salt or metal, right? So liquid sodium or so then you can burn uranium 238 and you can burn also plutonium in those fast neutron reactors. Okay, because the molten salt wouldn't, it would be good for just this fast neutrons to get them to the right speed so that we split 238. Alright? So actually if the neutron is too fast, what happens is that he will go through the atom. But you actually want to slow him down so that he can get captured. And then make it unstable and then split it. Okay? Yes. So this is probably the older number. So are the numbers a little bit higher? Yeah. So I think your number are more recent. Yes.
What's the number of GW stand for?
So gigawatt, I guess,
The number
is the number of nuclear reactor that exists in this design already. So here is a sketch of those designs. So sometime in the final exam I have multiple choice. And so in the multiple choice I will show you something like this and I will tell you basically label which is which. So how could we tell which is which? I mean, if you see sodium going between the reactor, the fuel and the steam, that is obviously fast breather basically, reactor. Okay? And it's called breather because it breathes its own fuel. So he will turn 238 into plutonium while he's doing this. So that is really good technology because eventually we will run of 235. So sooner or later we have to figure out a good design to start burning 238. And if you see graphite sitting in the reactor, so he's cooling with water, but he has around the fuel rod, he has graphite everywhere as a moderator, right? So this would be a graphite moderated water cooled reactor. Okay, you see gas going on and graphite, this would be gas cooled, right? And if, I guess the heavy water reactor, you will not be able to tell unless they tell you that it's having heavy water. So when you see heavy water sitting over here, you would know that then that is the Kando design. The heavy water reactor, it's called Kando for Canadian something. Right? So this is the one that exploded in Fukushima, and that's from General Electric, and that is actually the design that we have in a lot of our power plants. Okay? So what is going on? Water come in and steam leave from the top. Okay? So water come in and steam leave, and you can see the guy in, what is that on the top? Steam trap. This is like any steam power plant. When you make steam, sometimes tiny droplets get carried out, right? So at the end of the drum, you always, the steam drum on top of the boiler, before you send the steam to the turbine, and the turbine has plates and rotating very fast, you want to capture any flying droplets with the steam. So you build this so that basically the steam only goes through and droplets basically get hit by the wall, drop down. Okay? And under it, this will be where the fuel rod is, and coming from the bottom is, what do you think, 24? What those things hanging ready to get inserted in? Those are the control rods. And for safety, you can see that he has an external cooling circuit that basically, in case that water coming from the turbine does not from turbine, coming from the condenser and the pump and the feed water pump, if this thing does not come around, basically he will be running those cooling circuits, right? And this can come with like big tunnel of water that basically can supply a lot of cool water that can go in and cool the place on demand. Okay, so because this turn water into steam, this is called boiling water reactor. Boiling water reactor. Wouldn't always be boiling water reactor? No, if the pressure here is high enough, the water can get hot without boiling. Okay, so it becomes pressurized water reactor. So this is boiling water reactor, and the pressurized water reactor will be something like this. So that's also important for multiple choice. If you show this and I tell you, is that boiling water reactor or pressurized water reactor? Because the water that go into the nuclear rod, one guy actually 1 year, he told me it's easy. It's because he said, I got it because the control rod in the sketch was coming from the top, and in the boiling the control rod was coming from the bottom. That's how you can tell whether it's pressurized or boiling. But no, that's not. It's because the water is going into a closed circuit. Then you know that's not boiling. So it goes between the nuclear reactor and the boiler, the actual boiler. And in the boiler, that hot water, it's liquid but it's very, very hot. That water heat the actual water that turn into steam, into the turbine, into the condenser, on and on. Okay? So we can tell it's pressurized water reactor if we see the water going into the reactor never turn into steam, but instead going into a circuit of its own. Right? And this guy is a little bit safer, I would think, because the water never boil. So it can maintain its cooling effect basically. Unlike the other one, imagine what happened if all the water basically evaporate on you. There will be nothing to cool the reactor. Yes, the reaction rate will stop because there's no moderator, because we turn everything into steam, but still the decay heat need to be cooled, and it will not be cooled if you remove all your coolants. Okay. And so here is a sketch of the pressurized water reactor. So the core itself will have hot water leaving, cooled in this place, come back to him as liquid. Leave as liquid, come back as liquid. Leave as hot liquid, come back as cold liquid. And what happened on those things? Those things are a heat and tube heat exchanger. The hot water coming from the nuclear reactor come in, go into the tube, and come back into a place surrounded by water that actually boil and turn into steam on the top. Right? So you have 4 heat exchanger, that's each one of them being heated by the hot water coming from the reactor. Okay? And so here is, we talked about the Fukushima thing in 2011, and you can see what happened here. 3 of them exploded because the hydrogen made the fire, and 1 of them was still on fire. And here is the tsunami wall that was supposed to protect you, right? And so the company that basically built this thing, they decided that they basically said, we did just like was act of nature, like we never expected tsunami wave that high, and we built everything according to code, and we did everything right. It's just like unfortunate event. So their Congress, I guess in Japan, they made a committee to inspect what happened. and what is the reason for this accident. And the head of the committee was actually a medical doctor. He was not an engineer. And they went through all what happened and the reading and stuff, and they came up with a report. And that report, they said that problem was made in Japan. He said we actually have to claim responsibility for it, and it's mainly because they call it groupness thing, and like how like we as society tend to be like stick to the group and never question authority. And there was a lot of things in that design that no one ever dared to speak up against or even try to and so they basically said that it was us. It's just that we never really open ourselves to external reviews. We always tend to like stick with the company, you know, and that was not really right. So here is, so that the problem again, so that maybe from society point of view, that's what happened. But from engineering point of view, what happened in that design was, here is, you can see the nuclear reactor, right? And this big torus here, this is filled with water that is ready to, with all the pumps, keep flooding this thing with water. See, this is the nuclear reactor and there is all this water. And those chamber here, filled with water, what is that? What do you think this thing is? Anyone? This is the spent fuel rod. So after you finish using them, you put them here underwater. Why you put them underwater? For cooling. They need to stay underwater for a bunch of years until they are cold enough. Then you can air cool them in dry storage. But they have to stay in water storage for a bunch of years. Okay, no reactors, right? But still need to be cooled. And so what happened is that spent fuel pool, basically the water was lower than it, and as a result you end up with explosions. So this is where we keep our spent fuel rods in the USA. Alright, and so a lot of reactors basically keep them underwater, and then after that they move to air storage basically. Okay, so in the US it's a home to 65,000 tons of nuclear reactor waste. Okay, and this grow by 2,000 tons each year. So every year 2,000 tons need to be stored, and you have to store them in. So the red is dry casket. After you finish cooling them in underwater. Okay. So fast breeder reactor. How does it work? So 235 break into two things, and then two neutrons leave, 2.5 kind of, and then this guy, if you can make him capture in 238, he will turn 238 to 239, and this 239 go to beta decay, another beta decay, losing electron, and so 92 become 93, 93 become 94, and that is plutonium. Okay, and so basically in a fast breeder reactor you are turning your 238 that's not fissionable into plutonium that is basically fuel for the next stage. Okay, so that is the appeal of the fast water. However, the moderator medium must exert low moderation, liquid sodium basically, for it to happen, and it will convert 238 into plutonium and fission plutonium. So I think I read one time that Bill Gates was funding a company that will extract uranium from the ocean, from the water, the sea ocean basically, the ocean water. So there are research going into building safer reactor, as I told you, like that is passively safe. Like you don't have to babysit them all the time. You just leave them and they are safe because they drop the fuel, spill the fuel, and also small enough that you can put them in small cities rather than one big guy that take forever. So the Department of Energy was funding research to build like small reactor that can be built in the factory, and you just ship them to Stillwater, to Parksville, to small cities around. Okay, and of course fast breeder reactor that can use the majority of the fuel. So the bottom line here is that nuclear energy is not inherently unsafe. No, it can be safe. It's just that you're designed to be passive, and you need extra redundancy of cooling systems so that you don't have to worry about the decay heat in case accident happens. Alright, and so let's take a 15 minutes break and we'll start at 9:05.